reason I concentrate on Schwarzschild black holes is because there's something very general about them. The properties of the horizon are very universal. Basically, all black holes locally near the horizon look exactly the same, unless they're extremal black holes. Extremal black holes are the odd ones. They're non-generic. They're very special. And they are useful in confirming certain things about black holes, but they're certainly not the generic things that either astronomers or anybody else other than a string theorist would consider a black hole. So my inclination is to follow as far as possible what we can find out about Schwarzschild black holes, and then at the end resort to whatever extent we need to extremal black holes to perhaps fill in certain pieces that we can't completely derive about Schwarzschild black holes. It's surprising that Schwarzschild black holes are in some sense harder than extremal black holes. Their horizons are much simpler. The horizon of a Schwarzschild black hole locally is nothing but flat space. We thought we understood everything about flat space. And the horizon of an extremal black hole is very, very odd. It's nothing like flat space. So it's a little bit surprising that it's harder, in some sense, to do quantitatively the properties of Schwarzschild black holes. However, the thing which makes extremal black holes particularly simple, not in general, but in very, very special contexts, is supersymmetry. I'm not emphasizing supersymmetry because I want to talk about black holes in more general context. That doesn't mean I don't think it's useful. It is. But let's return to some simple definitions. First of all, just some variables. There's small t, which is Schwarzschild time. S-C-H, and I can't spell the rest of Schwarzschild, but I can spell time. Schwarzschild time. And Schwarzschild time has the property that far from the black hole, it's just ordinary time. Far from the black hole, when you're a large distance, it's just ordinary time. So an observer very, very far from the black hole with an ordinary wristwatch will be measuring Schwarzschild time. Then there's omega. Omega is related to Schwarzschild time. It's just dimensionless. And by definition, it's simply t over 4mg. But it also happens to have the properties near the horizon of being hyperbolic angle. Remember, Schwarzschild coordinates, or the Schwarzschild time near the horizon, has the properties of a hyperbolic angle, except that you'll have to make it dimensionless before it becomes hyperbolic angle. So omega is hyperbolic angle. And it can also be called the Rindler time. I may not have used the word Rindler up till now, but we will use it. It's basically the near horizon geometry. Then there's rho. Rho is proper distance from the horizon, measured in the radial direction, proper distance. And the other variable that I used in order to describe the near horizon geometry, I called u, and u was nothing but logarithm of rho. U and omega together define conformal coordinates for the radial geometry. The geometry in the direction of the horizon, of course, is not conformal. Right? And the advantage of these coordinates are also closely related, namely u and omega. They're closely related to the tortoise coordinates. Apart from a normalization factor, near the horizon, they are the tortoise coordinates, u and omega. And in particular, u goes to minus infinity at the horizon. It doesn't pay to say what it goes to at plus infinity, because when u gets too big in the plus infinity direction, you're moving too far from the horizon. It still could be defined, if you like, to be proper distance from the horizon, but it's mostly useful near the horizon. All right, let me remind you now about the wave equation in region number 1. Region number 1 is what's called Rindler space. Region number 1, the wedge of ordinary flat space-time, is called Rindler space. And of course, the point is that near the horizon, as I've demonstrated several times, near the horizon, near a point on the horizon, the geometry is very, very close to flat space-time. And it will turn out that we can derive almost everything about the black hole. By studying flat space-time, the only reference to the mass, size, and so forth of the black hole is this connection between Schwarzschild time and hyperbolic time. All right, so let's concentrate then near the horizon. Here's the horizon over here, the extended horizon, this line over here. You're inside the black hole over here. Lines of constant rho, or any other one of the radial type coordinates are hyperbolas, and lines of constant omega, or time, look like that. They accumulate, and they go to omega equals infinity, or t equals infinity, on the light cone here. Next, an observation. All of physics in region 1 can be thought of as self-contained. I think I mentioned this, but let me mention it again. It can be contained, it's self-contained in the following sense, in that the conditions on the backward light cone, which of course might be determined by things coming in from the outside, but the conditions on the backward light cone can simply be thought of as part of the initial data at t equal, or at omega equals minus infinity, also t equals minus infinity. They can be thought of as part of the initial data. Things going out into region 2, I guess that's called, can be thought of as part of the final data at asymptotic infinity. And things in region 3 cannot communicate in any way with region 2. They can't send signals, or they can't receive signals from region 1. And so physics in region 1 can be thought of as self-contained in the sense that an initial value problem at t equals minus infinity will lead to unique answers anywhere. Now I'm talking about classical physics. Classical physics, classical wave equations can be formulated completely in region 1, which is the same as formulating them in terms of the coordinate u. U goes to minus infinity at this point. In terms of the coordinate u, omega, and let me add 2 more coordinates, x, x1 and x2. x1 and x2 are the coordinates in the horizon, in the tangent plane of the horizon, near a point, and they're just flat space coordinates, so just ordinary flat on the tangent plane to the horizon. They basically stick out of the blackboard, so the horizon sticks out of the blackboard. The radial and time-like directions are on the blackboard. Okay, let me remind you what the wave equation looks like in here. We're going to want to do quantum field theory, but first let's remind ourselves what classical field theory looks like. A minimally coupled scalar field chi has a wave equation in terms of omega and u, which just looks like d second chi by d omega squared. I'm taking the massless case. Massless case is the most interesting for us. Minus d second chi by du squared, perfectly ordinary Laplacian in 2 dimensions, plus k squared e to the 2u times chi equals 0, where chi now means the Fourier component of chi in the x1, x2 direction. K squared is the square of the momentum in the direction of the horizon. The larger it is, we're talking about things which vary quickly along the horizon. K equals 0, is basically, well, k equals 0 means in terms of particles, it would mean a particle with no momentum at all along the horizon direction. All of its momentum would be radially outward. So you can see from this formula that there's a potential barrier, and the potential barrier, horizon way out here, infinity way out here someplace. Okay. At some point, this wave equation breaks down because we're not really dealing with flat space, we're dealing with a black hole. I'll tell you about where it breaks down. It breaks down somewhere near rho of order mg. Rho of order the Schwarzschild radius. This equation breaks down. In fact, it tends to break down at about 3 mg. It breaks down badly at 3 mg. But up until you get out to a distance somewhat larger than mg, this description is pretty good. Okay? Now you can see that there's a potential, and the potential depends both on u, and exponentially increases, and it also depends on k. The larger k is, for a given frequency or a given energy, let's say, for a given energy, a wave can propagate a certain distance, and that distance depends on k before it gets turned around by the exponentially increasing potential. Okay, now let me just very quickly remind you, most of what we're going to do today is in Rindler space, but let me just remind you what does happen when you add in the full global structure of a black hole. In that case, the Rindler coordinates get replaced by, the omega and u coordinates get replaced by the tortoise coordinates. Right? For reasons which are somewhat historical, the tortoise time is taken to be t instead of omega, but the tortoise r coordinate is essentially u, at least near the horizon. It differs from it by a constant. It differs from it by a constant, but it is essentially u. Let me just remind you quickly what the difference in the wave equation looks like. First of all, it's conventional to redefine the field so that instead of writing chi, we write psi, which I think is r. Is it r times chi or chi over r? What are the other? I forget. I told you last time, I don't remember. It's the standard redefinition of a field when you go to polar coordinates so as to eat up the measure factor associated with the size of the sphere. So you go to a rescaled coordinate, a rescaled field psi, and then the wave equation looks very similar, except in tortoise coordinates, d second psi by the p squared minus d second psi by the r star squared plus or minus? Plus, I think. Plus v of r star psi equals 0, where v of r star replaces k squared e to the 2u. Now, of course, before I tell you that, I should tell you what replaces k squared. What replaces k squared is the angular harmonic psi Lm, where psi Lm is the coefficient of y Lm in the spherical expansion. Okay? What is the connection between k and L, roughly speaking? Well, it's the connection between momentum and angular momentum. You're near the horizon. Now, many of you probably have learned sometime in your past that angular momentum is equal to r cross p. So if you have a momentum parallel to the horizon, near the horizon, let's call it k now, then basically the angular momentum is just equal to the Schwarzschild radius, mg, or 2mg or whatever, times k. That's the rough connection between angular momentum and wave number and Rindler wave number. Okay? But what goes in here is a potential which depends on L. It matches closely the k squared e to the 2u as long as you're far to the left But as you move far to the right, it takes on a new character due to the fact that the metric far away makes the transition from the near horizon geometry to the far horizon geometry. Only important thing to know about V is its form. And even that is not terribly important. It's R minus 2mg. Remember that R star is some specific function of R. R minus 2mg over R times, and here's the important stuff, L times L plus 1. That's replacing k squared divided by R squared minus 2mg over R cubed. Now, one of the interesting things that's here is that even for L equals 0, there is a potential which falls off more rapidly at large R. In other words, it does not look like a centrifugal barrier. At large R, where this is 1, this just looks like an ordinary centrifugal barrier. Here's something that falls off at large R faster than the centrifugal barrier, but it's the pure S-wave potential. And there is an S-wave potential. Let's see, do I have the sign right here? The S-wave potential should be positive. I may have copied the sign down wrong. I have a feeling that this should be positive because the potential, yeah, the S-wave potential should also be positive. I may have copied the sign wrong out of my notes. Anyway, here is what the potential looks like as a function of L and R star. At large negative R star, it just looks like the exponential potential. And there's a series of them, one for each L. For L equals 0, it's the lowest of them, and it peaks, they all peak somewhere near 3 mg. Asymptotically, as L gets larger and larger, they peak at exactly 3 mg. Let's see, I think the S-wave one peaks at 8 thirds mg. So it's almost also 3 mg. And they look like this. And they have a certain height which increases. Right? From the outside, it looks like centrifugal barrier. From the inside, it looks like I don't know what to call it. Yes, I do. It's the gravitational field pulling things back to the horizon. And that's all it is. Okay. That's the basic setup. Notice one other thing. The S-wave, I could say the same sorts of things about the higher waves, but I want to concentrate on the S-wave. An S-wave quantum moving from the left, or for that matter from the right, will be able to cross the barrier. All right? If the frequency nu, let's look at this here. Nu, here's our equation. I'm using ordinary Schwarzschild time here, so when I speak of nu, I mean ordinary frequency as seen from a large distance, not frequency in Rindler coordinates, but ordinary frequency. That would be nu squared over here, and so if nu squared is bigger than v, or let's just write if nu is bigger than the square root of v, then a wave will pass freely over the S-wave barrier. For higher angular momentum, nu has to be yet higher. Okay? So what does it say? Square root of v near the horizon, square root of v near the horizon means something like 1 over mg. And so if nu is greater than about 1 over mg, there's some numerical coefficient there. In fact, it's 0.15. But some numerical coefficient, if the frequency is larger than that, it will just sail over the top of the potential. If it's a little bit lower than that, there'll be some little bit of tunneling barrier. And of course, if the energy of the quanta is very, very low, it will just reflect off the potential from either side. Okay, so that's the basic classical physics. One more classical thing to mention is the form of the Hamiltonian in Rindler coordinates. So let me draw again Rindler coordinates. Let's draw again Rindler coordinates and see if we can get some idea about why the Hamiltonian in Rindler coordinates is what it is. All right, there's our basic flat space-time. The Rindler time is a hyperbolic angle. Let me introduce coordinates. These are flat space coordinates now. They are none of the coordinates that we studied so far. They're simply ordinary time, which I'll call capital T, and I could call this coordinate Z, but I've already called it rho, so I might as well just call it rho, distance from the horizon. Remember, the horizon comes out of the blackboard, it's x and y, and capital T at the moment does not stand for temperature. Later it will stand for temperature. That's because I don't have enough letters in the alphabet. But for the moment, this just consists of a vertical upward coordinate on the Rindler plane, T and rho. All right, now if you're doing flat space quantum field theory, there is, of course, an energy momentum tensor, and I'm particularly interested in T naught naught. It's the energy density, and it's normally thought of as the energy density conjugate to the capital T. It's ordinary T naught naught. But an omega translation, this is what generates the integral of this over space. That would be d rho, d2x, and maybe even integrated to the left-hand side here also. That would describe the ordinary Hamiltonian, which shifts you from one time to another. But I'm interested in the Hamiltonian, which shifts you from one Rindler time to another. And notice that delta t is equal to rho delta omega. So the amount that you translate in time depends on how far you are out. And that tells you that the correct Rindler Hamiltonian, let's call it H Rindler, contains another factor of rho here. Another factor of rho. So it's the ordinary energy density, except weighed with a factor that depends on distance from the horizon. That's called the Rindler Hamiltonian, and that is the Hamiltonian that, that governs the near horizon equations of motion in Rindler space. I can write it down for a free field. For a free field, it's exactly what you expect. 1/2, now rho, d rho to 2x, integrated over rho and x. And then just the usual things, canonical momentum conjugate to the field, squared, pi squared being in quantum mechanics, it'll be d by d field, but in classical mechanics, it's just the conjugate momentum conjugate to whatever the field is. Then plus d rho chi squared over 2, and then plus dx chi squared over 2. This is just the usual energy density that you would normally write down. Canonical momentum squared, gradient energy squared, both in the rho direction and the x direction, except weighted with rho. Now, of course, one of the reasons I'm doing these things the way I'm doing them is I want to avoid completely the free field approximation. Right? So this was just an example. This is general. This is just an example, and so I want to get rid of it for now because I'm not really interested in free fields. We want a technique to understand Hawking radiation, all these things, without relying on free field methods. All right, now, can we do quantum field theory in the Rindler wedge in a self-contained way, without reference to any of the other, regions? The answer is yes, but we have to take into account one effect, and that effect is entanglement between the left wedge and the right wedge. Here's time t equals 0. Here's time t equals 0. By entanglement, I mean good old Einstein, Rosen, Podolsky, EPR entanglement, but just entanglement that's there in the vacuum. A vacuum fluctuation happens over here, sends out a pair of virtual electrons, electron and a positron. One goes here, one goes here. the effect is going to be to entangle the right degrees of freedom from the left degrees of freedom. Under those circumstances, we know what to do. We know what to do, which is to integrate out the left degrees of freedom and define a density matrix. In fact, let's label these. Let's call the right side A and the left side B. If we want to study physics within the right side, we introduce a density matrix, and then an equation of evolution of the density matrix within A by itself. But we have to calculate that density matrix because that density matrix is dependent on what happened in this backward light cone, as well as what may have happened in here. It depends on it, and so we have to calculate it. That's going to be our goal. We're going to try to calculate the density matrix corresponding to region A. So I think I need to tell you what a density matrix is. Most of you know, but oh, one last thing. One last thing. If you look at the fields, let's call the fields on the right side of the horizon over here, let's call them phi A, and let's call the fields on the left-hand side phi B. Then, for example, for just free fields, the correlation function of phi A with phi B, the equal time correlation function, phi A, phi B, is not zero. That's because there's entanglement. And it happens to be, for simple free fields, of order 1 over delta squared, where delta is the distance between these points. So the entanglement falls off with distance, but it's there at short distances. And so when you agree to ignore what's going on the left, you must account for it by inserting a density matrix which somehow knows that the left-hand side is entangled with the right-hand side. Okay. That's the object that we want to calculate.
Lenny, what model are you in?
No model.
No, but I mean, so you have the k squared and all of that.
Yeah.
And you still you write 1 over delta squared as if it's...
1 over, yeah, but okay, the coordinates that I'm now thinking about are t and we could call it z here. Right. So an ordinary flat space. This is just an ordinary flat space. We're now in flat space, and what we want to do is calculate the physics in the Rindler wedge here. The near horizon physics is guaranteed to be very, very close to the black hole, in fact, identical to the black hole. But then we're going to find out that we learned enough just by looking at the near horizon to tell us basically everything about the black hole thermodynamics. Okay. Oh, the other interesting point is that although the left and the right are entangled, they are not interacting. You might wonder, well, what do I mean by interacting? There are no terms in the Hamiltonian for the system, at least in the Rindler Hamiltonian, which couple the left to the right. You might think that there are gradient energies across this boundary here which couples the left to the right, but fortunately in the Rindler Hamiltonian, there's a rho which goes to 0 at this point here, and so it completely decouples anything on the left with anything on the right. And the Hamiltonian on the right-hand side does not involve the left degrees of freedom, but the state of the system has to be taken to be a density matrix. So let me just review very, very quickly the idea of a density matrix. If we have a system, and now I mean A and B together, the whole initial state of the flat space quantum field theory, it consists of 2 sets of degrees of freedom, A's and B's, and there is some ground state wave function, which I'll just call psi of alpha and beta. Alpha and beta stand for all the degrees of freedom in A and B. Okay? The density matrix of the A side of things, let's call it rho A. Well, the density matrix is defined as psi star of alpha beta, psi of alpha prime beta, summed over beta. That's rho alpha alpha prime. That's the density matrix where beta has been integrated out, but it still has 2 open indices, alpha and alpha prime. So it's an operator in the Hilbert space of the right-hand degrees of freedom here. Okay, the rule for density matrices, most of you know it. The rule is if you want to calculate an expectation value of an operator belonging to the right-hand side of things, the rule is that the expectation value of any operator which depends only on the fields on the right-hand side here, the expectation value of that is trace of rho times A, which is also equal to trace of A times rho. So if we could figure out what rho is, we would at least get a start on calculating some correlation functions or whatever we're interested in on the right-hand side. But we need to know one more thing. How does rho evolve with time from one slice to the next slice? And there the answer is straightforward. You derive it from elementary quantum mechanics. And the answer is that d rho by dt satisfies a kind of Schrodinger equation, except instead of the usual Schrodinger equation, it's equal to I times the commutator of rho with h. In our case, we're talking about the density matrix of the right-hand side, and this Hamiltonian is the Rindler Hamiltonian. That's the Hamiltonian which tells you how to evolve from one section to another. So this then would be the complete quantum mechanics of the right-hand side if we knew the initial density matrix. Now we can expect that if we're talking about the vacuum of flat space, that the density matrix will be independent of time in the Rindler sense. And the reason is, a Rindler time translation is nothing but a Lorentz boost from the point of view of the flat space coordinates. And if we expect the vacuum to be Lorentz invariant, that would translate into saying this rho of A is time independent. And it is time independent. But that's just a thing that we should keep in mind, that it is time independent. Nevertheless, it does satisfy an equation of motion. For example, if we perturb the density matrix away from the flat space vacuum, for example, by making some perturbation in here, we might then have an evolving density matrix, and this would tell us how it evolves. But if we're interested in just a neutral vacuum, the static, time-independent, equilibrium configuration, then we should find that rho A basically commutes with our Rindler Hamiltonian, and so it should have no evolution. So this has both. Yeah, okay, that's the starting point. How do we calculate the density matrix? That's the question. So let's begin with how we calculate the ground state. I'm going to write down a general formula for ground states. It's called the Feynman somebody formula. I can't remember who. That's terrible.
Feynman Hellman.
Yeah, that's right. Feynman-Hellman theorem. Right. Good. I think that's. I think I've got the right one. That's the one that tells you. Yeah, I think it's the right one. Feynman-Hellman. Here's the idea. Supposing I'm interested in the ground state of some arbitrary system. Okay. Well, take any state, any old state. Let's just call it A for any. Oh, I better not call it A because I've already used A. Let's just call it any. Any state. When I say any state, it cannot quite be any state. It has to be a state, a generic state, which happens to have a non-zero projection onto the ground state. But, you know, if you just take any old arbitrary state, the chances are we'll have a ground state projection. Then you multiply it by e to the minus ht. Now I'm thinking of t as being the vertical coordinate on the Rindler plane there, but it's time. It's not temperature, it's time. But it's not time either. It's not time, excuse me, it's not time. If it were time, I would put an I there. Right? So you just invent a variable t, a real variable. You can call it Euclidean time if you like, right? But it's t without the I, so it's actually Euclidean time. You just multiply e to the minus ht by any state whatever, and if you wait long enough, if you go to the limit of large t, limit as t goes to 0, this will evolve to the ground state. All right, to illustrate why that's so, let's just, well, not for arbitrariness, for definiteness, let's assume that the ground state energy is exactly 0. If it's not, we can always shift it. All right, so we can always write this as e to the minus et any summed over E, where E is the energy eigenvalue of the eigenstate E. Just a sum, let's introduce a complete sum of energy states in here. And now, every one of these contributions will go exponentially to 0. Why? Because the lowest energy state has 0 energy, all the other ones have positive energy. All of these will go to 0 except for the ground state. The ground state, which by definition now has 0 energy, will give us a contribution which will be 1 times the ground state times a number, and this is the ground state any projection. This is just a number. It won't influence anything that we do because we're eventually going to divide out by that number anyway. So if you take e to the minus ht and you multiply it by any state, you will eventually come to the ground state. If you're interested in the ground state projected onto some state of definite coordinates, these coordinates could be fields, they could be particle positions, they could be whatever the coordinates, whatever the configuration space of the theory is, then we can call this psi ground state of x. Psi ground state of x is just given by taking this matrix element and letting t go to infinity. All right. Now, how the devil are we going to do this for the problem at hand? It seems awfully hard, but it's not. Here is our Rindler space again. A, B. And all I want to do now, I'm going to use the vertical direction here to represent t. Now keep in mind, it represents an imaginary continuation of time. And I'm going to slice it up into thin slices and think of the thin slices, each one of them as being an e to the minus epsilon h. All right? So I'm going to divide this imaginary time into thin slices and then multiply together an infinite sequence of small imaginary time displacements to construct e to the minus ht. I'm not really going to do it, we're just going to pretend we do it. And in this way, we can think of the process as just a kind of transfer matrix process from one time to another in the vertical axis. Right. Now there's another formula which follows by path integration. If we think of each of these slices and then add them all together, we can convert this same matrix element to a path integral. And the path integral is obvious. It's a Euclidean path integral. And it's just the integral over all the fields in the upper half plane. Out here we have anything. That's our anything state. Okay, so we start with any initial condition at t equals infinity. We do a path integral over all the fields in the upper half plane of e to the minus, not an I, no I, but a Lagrangian composed out of the fields dt. And this Lagrangian is the Euclidean continuation of the Lagrangian in which t, or capital T I guess belongs here, in which we have set ordinary time to I times time. So everything is real, everything is completely real here, but with a boundary condition. This is the integral over all fields in the upper half plane of e to the minus the action, but with a boundary condition. The boundary condition is that at t equals 0 here, this integral, this action, goes from 0 to infinity. That's what corresponds to this over here. Goes from 0 to infinity. The ground state is being defined at t equals 0. Here's our path integral that represents the same physics as e to the minus ht, but we constrain the fields at the initial point to be phi A and phi B. So it's a path integral subject in the upper half plane, subject to the constraint of some initial data on the initial surface. And that's it. That is the ground state wave function, or wave functional, we can call it psi ground state, of phi B and phi A. The wave functional is a functional of the fields. I've divided the fields into two groups, A and B. And the ground state wave function is a function of phi A and phi B given by this path integral. Okay, it's a hard path integral. How are we going to do it? Especially how are we going to do it in great generality? Well, of course, we're not going to do it, but we're going to rewrite it. And to rewrite it, what we're going to do is take exactly the same path integral, but chop it up into little transfer matrices. Instead of transfer matrices transferring us from one layer to the next, they're going to be transfer matrices which transfer us from one angle to the next. In other words, we're going to use a path integral to take us from here to here, and then a path integral to take us from here to here, from here to here, and each time integrate over the intermediate degrees of freedom on the slices. Well, there's another way to write this. The other way to write this is to realize that there's a Hamiltonian which propagates us from one angle to the next. And that Hamiltonian is nothing but the Rindler Hamiltonian. It's the Rindler Hamiltonian because it translates you a distance which is proportional to rho, which is proportional to the distance from the horizon. So the generator of these rotations in Euclidean space, which rotate you from one omega to another, is nothing but the Rindler Hamiltonian. We don't propagate the system in real Rindler time. We propagate the system in imaginary Rindler time, and imaginary Rindler time means angle. So we can rewrite this. We can rewrite this matrix element as a transition amplitude. A transition amplitude where we start, let's see, let me get this right. Let's start with the data on this side being called A prime. It's a transition matrix element from the state A prime. And A prime simply means the values of the fields here. The values of the fields phi A prime. We start with state A prime. We evolve it with the Rindler Hamiltonian, e to the minus h. Now, not t, but omega. This is h Rindler, omega. How far do we evolve it? We evolve it, and this is imaginary omega, so we might call it theta, angle. How far do we evolve it? We evolve it by angle pi. So we have angle pi here. We evolve it all the ways to the other side here and project onto the state B. B stands for the values of all of the fields in the B half of the space here. That is the wave function. Let's just call it psi ground state of B and A prime. It's a formal expression, but it's been written in terms of the Rindler Hamiltonian in a way that does not depend on any particular model. It doesn't depend on whether we're doing QCD or any quantum field theory at all. This is an exact expression for the wave function of the ground state in terms of the Rindler Hamiltonian. Okay, now let's go to the density matrix. The density matrix, we want to multiply this by psi star, same ground state psi star, of BA, psi ground state of BA prime, and sum over B. All right, so all we have to do now is write it down. The first factor on the right, that's just A prime e to the minus h pi. I'm going to stop writing h Rindler because it'll be the only Hamiltonian for the moment. E to the minus h pi b. But then the complex conjugate, all we have to do is interchange bras and kets, everything else is real, would be b e to the minus h pi again a. Can this be read? It's a prime, propagate by amount pi to b, but then multiply by b and propagate back to a. Not from a prime to a prime, but from a to a prime. From a prime to a. This is the product of the wave function with its complex conjugate, except leaving the indices a and a prime allowed to be different. Well, then we have to sum on b, and summing on b just removes the identity here. And so what do we get? We get a e to the minus 2 pi h, I'll now write Rindler, a prime. Another way to write this is that the density matrix of the degrees of freedom A, let's call it rho sub A, is nothing but e to the minus 2 pi h Rindler. Any experiment that you do on the A side is governed not by a pure state, but by a density matrix which has the form of e to the minus 2 pi h Rindler. Now, this would not be very interesting in general if we actually had to make computations with some complicated Rindler Hamiltonian. The point that makes this interesting is that this is a thermodynamic density matrix. The thermodynamic density matrix for Rindler Hamiltonian with a temperature, T, which is equal to 1 over 2 pi. Let's call this T Rindler, which is 1 over 2 pi. In other words, the self-contained physics in the Rindler wedge is the physics of a thermal ensemble. It doesn't mean you can't kick it out of equilibrium. It means the initial state is a thermal ensemble with the Rindler Hamiltonian being the correct Hamiltonian at a temperature of 1 over 2 pi. If you want to kick it out of equilibrium, you can do so by calculating real-time correlation functions and so forth. Various specialists in that subject, like Schwinger and Kubo and Braut and other people will tell you exactly how to do that. I assume you still remember how to do that.
Maybe I remember.
Maybe I remember. I'm sure you knew the whole time. But this is the setup. Thermal equilibrium at temperature 1 over 2 pi.
So,
Yeah.
use the fact that this is the ground state description. If I had an excited state, how would this derivation work?
Well, say it again, say it again.
I mean, where have you used the fact that you had the ground state? I mean, understand where that went to.
Where did it go into it? So it went into it by using the Feynman-Hellman formula to count it. I'm not sure what you're asking exactly.
Yeah, just
Yeah.
think about it a bit more.
Right, so that's the physics of Rindler space, but very, very close to the horizon, the black hole is Rindler space, and so we expect that very close to the horizon here, an observer will see exactly a temperature of 1 over 2 pi. Now, wait a minute, 1 over 2 pi. 1 over 2 pi in what units? 1 over 2 pi, is it Kelvin? Is it Celsius? Is it Fahrenheit? Is it Planck? The answer is, it's none of those. It's a dimensionless temperature. Why is the temperature dimensionless? The temperature is dimensionless because the time variable omega is dimensionless. If time is dimensionless, then its conjugate variable energy is dimensionless. If energy is dimensionless, temperature is dimensionless. Well, this is not the temperature that you measure with a standard thermometer. A standard thermometer has energy levels, proper energy levels. This is not the proper temperature measured by a proper thermometer at a given distance from the horizon. So let's talk about the proper temperature. What I do want to emphasize before I do that is how just that this is, I've said it several times, let me just say it once more, this derivation in no way relies on free fields, on Boggle-Ubug transformations, on anything special. It would apply to any quantum field theory, any local quantum field theory, Lorentz invariant, no matter what it was. Now, whether it would apply to quantum gravity, that, of course, is something we're making an assumption about, because we don't know very much about quantum gravity, but this would be the right physics for any quantum field theory, whatever. Okay, so now let's discuss.
Also, when the black hole is not collapsed.
When it's what?
Like if you drew it last time.
Yeah.
You have to prove that this is applicable.
Yeah, I think we should have to prove it, but let me say, the time when it's applicable is long after the collapse. When black hole is settled down to an equilibrium state, the equilibrium state looking very much like the...
Are you suppose or you prove?
I suppose. I proved. I think at some point I proved it, but it may even be in my book, the proof of it, but there's always the assumption that you've waited long enough for the black hole to equilibrate. Okay. And so that there is any proof whatever of the Hawking radiation and so forth, in generality, I think just about is as close as you can get. Certainly the methods of Hawking and so forth, which are extremely brilliant, are very, very special for free fields and would not apply to anything interacting. This derivation, which is, it's of course closely related to the Unruh derivation, but again, the Unruh derivation was free fields. Right, so this is a derivation of the Unruh effect, which is general enough for our purposes. Okay. Now let's talk about proper temperature as seen by a thermometer, a standard thermometer made in the standard thermometer factory, not the Stanford thermometer factory, the standard thermometer factory, which measures temperature in real energy units. So to understand how to go from coordinates, you could call this coordinate temperature. To go from coordinate temperature to proper temperature, you first of all really only need to know the proper time along at a fixed position. Proper time, we hold the thermometer fixed at a fixed position outside black hole or outside Rindler space. The tau is equal to square root of g0 d omega. Okay, where square root of g0 is whatever it takes to go from tau to omega. I'll remind you what they are. Square root of g0, or just g0, square root of g0 near the horizon is just equal to rho. That's the statement that the tau squared is equal to rho squared the omega squared near the horizon. So near the horizon, g0 is square root of g0 is rho. Far from the horizon, way out asymptotically, square root of g0 is 4mg. That's just a statement that very, very far away, proper time is nothing but Schwarzschild time, and Schwarzschild time and omega are related by a factor of 4mg. Okay. So these are the two g0s that we'll be interested in. But this is the relationship between proper time and coordinate time. Right? The conjugate relationship, and that would be the relationship of energy. Energies, proper energies, let's call them proper energies measured at a certain point, proper energies, let's call them B proper, would be 1 over square root of g0 times, let's call them Rindler energies. Same thing for temperature. Temperature is measured in units of energy. So proper temperature is 1 over square root of G naught naught T Rindler. T Rindler is the thing which was 1 over 2 pi. So now we can read off some more physical values for the temperature. The proper temperature near the horizon, we'll use this formula here, is 1 over 2 pi rho. In other words, as you get closer and closer to the horizon, the temperature gets larger and larger, diverging at the horizon. You should keep away from horizons. They'll burn you. What about very far away? The observer who is very, very far away, looking at the black hole, there, the operating value of G naught naught is 4 mg. So let's talk about the temperature at a great distance. It has a name. It's called the Hawking temperature. T Hawking, the temperature very far away, is just 1 over 2 pi times 4 mg in the denominator equals 1 over 8 pi mg. Notice that it decreases with mass. The 8 and the pi, as far as I can tell, have no special significance except, well, where are they inherited from? They're inherited from the fact that the circle has a, the angle goes from 0 to 2 pi. The 8, well, okay, that's, and the mg, that's just dimensional stuff. Temperature in units, ordinary units, has units of energy, and energy has units of 1 over length. Mg is a length, and so that's it. I have not included all the real factors in here. I think I should do so. I think at this point I should probably put in the h bars and the c's. There's an h bar in the numerator. It's a quantum effect, number 1. And there's a c cubed, speed of light cubed. There is also a Boltzmann constant, but Boltzmann's constant, it's kT really, which is, but I'll work in units in which temperature is energy. Okay, this is the Hawking temperature. The temperature is seen from very, very far away of this black hole. And if you were to work it out for a black hole of solar mass, because the mass is in the denominator here, there's a big number in the numerator, c cubed, there's a tiny number, h bar, and then there's a huge number, mg, in the denominator. And so if you work this out in Kelvin, degrees Kelvin, for a solar mass black hole, I think it's something like about 10 to the minus 8, 10 to the minus 8 degrees Kelvin for a solar mass black hole, or stellar mass black hole. And the bigger the black hole, the colder it is. Now, we're going to come back to that soon enough. But let's now consider the thermodynamics of black holes, the implications of a temperature. In particular, the most spectacular implication for me is that there is an entropy. So let's work out the entropy of the black hole using thermodynamics. Nothing but simple thermodynamics. And then later we'll talk about what the great implication is of the fact that there's entropy. Incidentally, the entropy, the fact that a black hole has entropy is not due to quantum mechanics. Quite the opposite. The fact that the black hole has a finite entropy as opposed to infinite entropy is what's due to quantum mechanics. So let's see if we can work out the entropy. Or we use the good old thermodynamic relationship, dE equals TdS. When I teach black holes and I have a little more time, and I'll probably get around to doing this, I really first teach what entropy is. Entropy is hidden information. It's measured in bits and all that kind of stuff. And I always think of temperature as a very derived concept. The way I think about it is that the temperature is the change in energy of a system when you add 1 bit of information. All right, but since we haven't talked about entropy and information yet, This is pure thermodynamics, the E equals TdS. Energy is mc squared, of course, but I'll leave the C's, I'll put back the units eventually, but let's just leave it out for a moment. Energy is m, T is 1 over 8 pi mg, and ds is just ds. Our purpose is to calculate the entropy of the black hole. So we now have a simple differential equation, 8 pi g dm squared over 2 is equal to ds, or just that entropy is equal to 4 pi m squared g, I believe. Is that right? 4 pi g m squared. Yeah. That's without units. I've kept the gravitational constant around, but if I want to put back standard units, there is an h bar in the denominator and a c. Now the h bar in the denominator is the interesting thing, that entropy, in some sense, is not due to quantum mechanics. Entropy is controlled by quantum mechanics. It's kept from being infinite. If you take the h bar equals 0 limit, the entropy of the black hole diverges. So we should think of entropy as being kept small by quantum mechanics rather than being due to quantum mechanics. Why would the entropy of a classical black hole, well, we'll come to why the entropy of a classical black hole would diverge. This is the bit, all right, now, last point about entropy is the famous connection with area. If we use the fact also that the Schwarzschild radius, R Schwarzschild, is 2mg, and if I really wanted to get it right, I would put c squared in the denominator. If I use the fact that the Schwarzschild radius is 2mg, well, first of all, you see the Schwarzschild radius is proportional to mass. Mass appears squared here, so it's evident that there will be some area in there. And if you work it out in terms of area, area being by definition 4 pi r Schwarzschild squared, then you can rewrite this in the famous form that S is equal to the area of the horizon divided by 4g, Newton's constant, h bar in the denominator, and I forget how many powers of c. I cannot remember how many powers of c, so we'll set c equal to 1. This can also be written as the area divided by 4 times the Planck area. Why 4 times the Planck area? I would say that the reason the 4 is there because somebody foolishly defined the Planck area, the Planck unit, without the appropriate factor of 2 to get rid of this. It's pretty clear that 4 times the Planck area is the fundamental unit of, but we're stuck with history, and so that reads the area measured in Planck units 1/4. 1/4 of a bit of entropy per Planck area. Okay, let's next, let me stop here for questions.
Well, yes.
Before you do, let me just sympathize with your question before. There is something missing here in the precise connection between black holes and Rindler space. There needs to be a step that has to be filled in. The step that has to be filled in is to explain why the black hole asymptotically in its static behavior tends to the Schwarzschild black hole, which has the property of a Rindler horizon, and that's a step that needs to be filled in. Anyway.
The identification of E with M,
Yeah.
that's tied up with the initial assumption, I suppose, that you begin with Minkowski vacuum.
That's right. That you begin not this Minkowski vacuum.
It's the mass that appears in the metric.
Absolutely.
And that's tied up with
That's
the
right.
initial assumption.
That's right. So it's the mass, as observed by an observer far away calculating the gravitational flux through a big sphere, the ADM energy, exactly. Right. Absolutely. Let's see if we can understand the luminosity of a black hole. Now, there's one way to calculate the luminosity of a black hole, which is very easy. You just use the Stefan-Boltzmann law. You write area times t to the fourth. But it doesn't really make a lot of sense. And the reason is that the luminosity of a black hole is extremely different than the luminosity of the sun. Here's an example. We're going to see that the luminosity of a black hole is entirely due, or almost entirely due, to S waves. Okay? The luminosity of the sun, here's the sun, it's emitting particles this way, it's emitting particles this way, it's emitting particles practically tangent to the horizon this way. They have all kinds of angular momentum. And counting up all of that luminosity is counting up basically everything. The Stefan-Boltzmann law is really the law which follows from physics like the surface of the sun. What's happening here is that the wavelengths are so long that they're basically as big as the horizon. The temperature, we'll see, is such that it's about the inverse size of the horizon itself. The waves that are being emitted are as long as the horizon itself, and they're all S waves. So it's a very, very different physics than the physics of the Stefan-Boltzmann law was designed for. Okay. My inclination is to go back to, where is it? Do we have it here? Is to go back to essentially this picture here, except in tortoise coordinates. So in tortoise coordinates, we see at about 3 mg a peaking of these functions, and in particular, the S wave function peaks like this. This is the tortoise coordinate horizontally. Vertically is the potential V. And if you remember, what I told you is that a quantum, all right, so what do we have? We're way down near the horizon here. Way down near the horizon, our temperature goes as 1 over rho. As we move into this direction, the temperature, the proper temperature goes down, but in this kind of Rindler setup here, where my coordinate time is omega, that either omega or Schwarzschild time t in tortoise coordinates, the temperature is actually constant. The coordinate temperature is constant. So the coordinate temperature, which corresponds to the wave equation, all those things, is a constant coordinate temperature, and the constant coordinate temperature in Schwarzschild units is 1 over 8 pi mg. That means that a typical quantum in the thermal ensemble on this side here has an energy of about 1 over 8 pi mg. It's bigger than that. It's somewhat bigger than that. The typical, but it's of order 1 over mg. The typical thermal quanta that are hiding behind this barrier here and that are there because the system is thermal in this region. All right. Question, how many of them get out per unit time from this thermal bath? This thermal bath in here is called the atmosphere, the thermal atmosphere of the black hole. It's full of quantum of all angular momenta. The higher the angular momenta, the deeper into the black hole they are before they get reflected. And the S waves are the ones that stick out the furthest. All right? The energy of every one of them is of order 1 over mg, the typical quanta for every angular momentum. Which ones get out? The ones that get out are basically the S waves. All of these potential barriers are very high by comparison with the typical energy of a quantum in the thermal bath. Only the S wave barrier is about the same height. It's even a little bit higher, but of course it's a tail in the Boltzmann distribution. And so from the tail in the Boltzmann distribution, there is a rather high probability, I forget what it is, I think it's about 3/4 or something, that a typical thermal quanta coming from the left will pass through the S-wave barrier. The probability of it passing through the P-wave barrier is small, I don't remember exactly what it is, and the property of it passing through the D-wave barrier is completely negligible, exponentially small. So the only quanta that get out are the S-wave quanta. Now, how many of them are there? Yeah.
Is it still true if you have really small m?
If you have really small, well, when you have a really small m, how small? Planck small? I think it's true down to any smallness where you can even think classically about the shape of the horizon and so forth. Yes, I think it is. But when you get down to places where the physics is unknown, Planck scale, well, but it's very hard. How on earth is an object as small as a Planck scale going to emit a thing with an angular momentum very big? It would have to have a large impact, assuming, actually, it has this very tiny thing. It wants to emit a large angular momentum, but let's assume that the momentum is bounded, it doesn't get much above the Planck energy. To make a big angular momentum in that case, you have to emit it far with a large impact parameter. So my guess is that it continues down to the smallest black holes. If you think about what that means, incidentally, it means that a black hole with a temperature capable of emitting optical light would have a radius equal to about the wavelength of the optical light. So it's a very, very tiny little bright spot, okay? 1,000 angstroms large at a temperature, visible light. You couldn't see it. It'd be too small to see. Okay, so we're going to talk about the luminosity. So the only things that get out appreciably are the S waves. Now, the S-wave particles, assuming a massless wave equation, move up and down this axis. I think I'll put in here T and R star and V. They move up and down this axis with the speed of light. How many are there per unit length? How many quanta are there per unit length here? And the answer is controlled by the temperature. The temperature has associated with it a thermal length, which you can roughly think of as the distance between photons. Okay. Right. And so the distance between photons is characteristic of the thermal length. And what is the thermal length? Well, the thermal energy is 1 over mg. That means that the thermal length is about mg. In other words, about the size of the black hole, the horizon size. So these particles are separated, roughly speaking, by about R Schwarzschild in these units that we're using. Okay? They move back and forth. Sometimes they go forward, sometimes they hit the barrier and they go back. They have a pretty high probability of penetrating the barrier here. So how many per second penetrate the barrier? Well, we know the distance between them, we know they're moving with the speed of light, and we know their energy. Okay? We know their energy is characteristic of the temperature, 1 over mg. We know the distance between them, of order mg, and we know they're moving with the speed of light. With a little bit of effort, everybody here can calculate how many of these particles get out per second, and then knowing the energy of each one of these, you can calculate the luminosity. I'll write down the formula for the luminosity. This is an order of magnitude. Of course, it depends on the details. It depends on how many different species of quanta there are, and so forth and so on. So I'm not giving you any kind of detailed, precise calculation. That would depend on the details of the physics. The luminosity is of order 1 over mg squared. I'll tell you where the 2 mg's come from. One of them comes from the distance between the particles, and the other corresponds to the fact that each particle has an energy of order 1 over mg. That's where it comes from. Luminosity means the rate of loss of energy. Now, you've got to put some C's into it, and maybe some H bars and things, but in units with C equals H bar equals 1, the luminosity is of order 1 over mg squared. Knowing the luminosity, we can calculate how fast the black hole loses energy, and we can ask how long it takes for it to radiate away an appreciable fraction of its energy. So that's easy. You just write that the rate of change of energy, which is the rate of change of mass, when C is equal to 1, is equal to minus, because we're losing energy, 1 over m squared g squared. And we can then find that the time to lose an appreciable fraction of its energy, let's call it T evaporation, is of order m cubed g squared. M cubed g squared is the typical time to lose, let's say, half the energy of the black hole. It's also the order of magnitude time for it to lose all of its energy. But to lose any appreciable fraction, it takes a time of order m cubed g squared. Now, as I said, there's some. Can anybody see where the constants go? I can't without doing it. But I can tell you how long it takes for a solar mass black hole to evaporate. And the answer is about 10 to the 60th years. Very long. But let me just say right now, a solar mass black hole is by no means evaporating. A solar mass black hole would have a temperature of about 10 to the minus 8 degrees. The ambient background temperature is 3 degrees. And so every black hole in the universe at the present time is so cold that it's accreting energy, it's not evaporating energy. We have to wait a long time until the expansion of the universe cools us down below about 10 to the minus 8 degrees before it even starts to evaporate. So evaporation is a long time project. Okay, what I want to talk about next, I think I'm going to stop now and take any questions or else just go to lunch. But what we're going to talk about next is information. Information, entropy, the relation between information and entropy, and the whole story of whether information is or isn't lost in black holes. The real puzzle, from a certain point of view, is the fact that the black hole horizon appears as an extremely hot membrane. We find that the temperature goes as 1 over rho. Sounds like it's a mighty dangerous place to fall into. And in fact, if there's anything consistent about the description that I've given you up till now, anything that falls into that region, as seen from the outside, must get boiled, fried, ionized as it gets deeper and deeper in, and eventually scrambled over the whole horizon. If this temperature means what temperature ordinarily means. On the other hand, the equivalence principle tells us that anything that falls into a horizon, if the black hole is big enough, will simply sail through without any harm at all. That's the tension, and that's the paradox, and that's the thing that we want to see if we can understand. So we'll talk about information next time. It's loss, what it means to lose information. It means disaster. It's not a good thing. Okay, good. Any questions? Yes.
When you having this type of wave equation in this coordinates, would it sort of reduce to something like a Regge-Wheeler type of differential equation?
Which kind of equation?
Regge-Wheeler.
Regge-Wheeler. I don't know what a Regge-Wheeler equation is.
It's this type of radial Schrodinger equation which incorporates angular momentum.
I see.
The reason I was asking is for S phase L equals 0. In principle, you can get a relationship in terms of how the phase varies, implemented.
Well, but since I don't know exactly what a Regge-Wheeler equation is, I don't know. But my guess would be it would be basically this equation in tortoise coordinates. That's what I would think. And then, of course, there is the problem of computing the penetration of the barrier That's where the great body factors come from and all that kind of thing. Yeah, is that what you're talking about? Yeah, if I had to guess, I would guess Regia Wheeler means the equation in torus coordinates. Actually didn't know that.
Would the still give a type of bound on how the phase of solution would change the momentum, the small values of momentum?
Well, I'm sure you can calculate it. You want to calculate what time delay? Or,
Yeah, right.
Yeah. I'm sure that I'm sure you can calculate it. But the interesting observable quantity that's calculated is the great body factors. But it's very interesting, and we're going to come back to it, that at very, very low momentum, the black hole absorbs nothing. It's a perfect reflector. And that's going to show itself up, if we get time, in the electrodynamics of the black hole and in the computation of its resistivity and so forth. But I hope we get to it, but if not, good. Okay.